Welcome to the training slides on using metadata for name. A large part of the skill of name is due to the input meteorology, and the old saying rubbish in, rubbish out applies here. So if we use the wrong metadata, if we put rubbish metadata into name, then we're going to get rubbish results. And large errors can develop if we use the wrong meteorology. Therefore, it's really important that we select the most appropriate metadata for the application that we're using name for. So by the end of this lecture, you should be able to describe how metadata is used in name, how name uses that metadata in order to compute the location of the particles. You should be able to select the most appropriate metadata for use in name for the application you're using name for. And you should know where metadata for name can be found, and that might depend a little bit on what other compute facilities you have access to, but I'll explain that as we go forward. So, how does name use metadata? Well, as a Lagrangian model, the metadata for name is completely offline, so there is no feedback from name to the metadata. The metadata variables are stored as gridded data and then interpolated to the space and time of location of each particle at each model time step. So each particle can in fact experience its own weather. So consider that we have a particle at a particular location. That particle will then query the weather database to find out what the wind speed, wind direction, precipitation, cloud, temperature is, all at that location. And then it will use that information in order to decide where it's going to move next. And that's true for every particle within name. So name can use a variety of meteorological data. Currently we're using two resolutions of metadata at the Met Office. We're using a global metadata which has a 10-kilometre resolution and it provides a forecast out to 6 days. And we're using a local UK metadata which has a 1.5-kilometre resolution but is limited only to the UK and has a 36-hour forecast. Name is also able to use a variety of other meteorological data sets. So for example, we can give name some single site kind of surface, near surface observations and name can migrate the particles using that metadata. It's also possible to use ECMWF data, and that's either operational forecast data from ECMWF or the large stores of reanalysis data that are stored at ECMWF. And then on top of that, we can also use ensemble metadata, so from a meteorological ensemble, or we can use metadata from other weather models, such as WRF or Harmony. So in order to make the most accurate predictions of where the particles are going to travel, NAME uses a large number of MET variables, which we've extracted from MET meteorological forecasts. We can see them all listed here. On the left-hand side, you can see we've got a number of three-dimensional fields which vary in X, Y, and Z. And on the right-hand side, we've got fields which only vary in X and Y. So on the left, you can see fields that you might expect, so the wind fields, but also fields like temperature and specific humidity. And then on the right, you can see where we've got the precipitation fields and the cloud fields and the pressure fields. So for more complex problems, it might be that you want to use two different resolutions of metadata. So you want to zoom in on a particular area and use high resolution metadata, but you also want to capture the large scale flow. And it's possible to do this in NAME using what we call a nested structure, so that you can use a high resolution MET in the center of your grid, and then you can use a lower resolution metadata further out from your grid. So you can see here in the top right hand corner, we've got a high resolution grid just over the UK, and then we've got a coarser resolution grid which we're applying here over Europe and the North Atlantic. And you can also nest metadata in time, so it might be that you want high resolution metadata initially in your run, and then going further out in time you might want to move to coarser resolution metadata, and that's also possible in NAME. So finally, you can also use radar rainfall data. So this would need to be used with some other metadata since it only provides precipitation data, but you can effectively replace the precipitation data from the meteorological model with precipitation from radar data. Now, I'm not going to go into all the specifics of how you specify metadata in name, as it's rather complicated. We'll come across that in some of the examples that we're going to do in the afternoon sessions. But just to let you know that each NWP numerical weather prediction model data type has its own MET definition file, which contains details of the grid sizes and the temporal resolution and the vertical structure. And you'll find examples of these MET definition files in the folder resources/defns, DEFNS. Each metadata type also has its own corresponding topography file. Because the topography doesn't change by time step, we've chosen to extract the topography. You may have come across Lagrangian models where the topography is stored with the metadata, but in order to save space, we've chosen to store it separately. So you'll find topography files related to each NWP dataset in the folder resources/topog. And all of these are, both this and the MET definition file, need to be specified in the input file so that NAME knows where to find them. And as I said, that's about all I'm going to say. So if you want to find out more information about the metadata, the best place to look is the user guide for NWP. So we've looked at how NAME uses metadata, but as I mentioned at the very beginning, it's really important to select the correct metadata for the application we want to use NAME for. So what do we need to consider if we're going to choose some metadata? Well, clearly it needs to be valid for the region we're interested in, and it also needs to be valid for the time period we're interested in. But there are also some other things we might want to consider. So the first thing we're going to consider is the impact of resolution on our run. And just as a first example, we're going to look at what the impact of that resolution is on a 10-meter wind speed forecast. So up here in the top left-hand corner, we have a 25-kilometer resolution Met grid. In the top right-hand corner, we have a 12-kilometer resolution Met grid. In the bottom left, it's 4 kilometer, and in the bottom right, it's 1.5 kilometer. And we can see that as we move from 25 kilometers through 12 and 4 kilometers to 1.5 kilometers, the picture showing the wind speed looks a lot less blocky, and we get a lot more detail in the wind. And in particular, we can see that impacts on the wind speeds along the coastline. So in the 25-kilometer grid, we can see here we've got this very straight coastline wind speed change. And if we look at the 1.5 kilometer, we can see that there's a very jagged edge to the change in wind speed at the coastline. So now let's take a look at an example of how the resolution of the metadata affects the air concentration that we might predict using a dispersion model. But before I get going with the example, I'd just like to point out that we use the topography file that associated with the metadata file, and so this means that the resolution of the topography is actually the same as the resolution of the metadata. So therefore, we're going to see, for coarse resolution models, we're going to see a coarse resolution topography. So what I've got here is an example from the Euro 4 model and from the global model. So on the left-hand side, you can see the example of the topography of Iceland from the Euro 4 model, which had a resolution of 4 kilometers. And on the right-hand side, you can see the topography of Iceland from the global model, which at the time of this slide had a resolution of 17 kilometers. And you can see the differences between the topography. So the topography in the 4 kilometer Euro 4 is much smoother and more rounded, and there are more features visible. And the resolution of the topography in the global model appears much more blocky, and there are really only kind of a couple of high points that you can distinguish in Iceland. So the example we're going to look at is a release from a vent just to the northeast of Barðabunga. So Barðabunga here is marked by the cross, and you can see the vent location, which is the small triangle just to the northeast of that cross. So first, let's have a look at the wind speed, wind vectors, and the sea level pressure for that region. So we've zoomed in here, so we can just see the small region around Barðabunga and the vent location. And you should just be able to see these in the center of each image. We're looking here at wind speed and wind vectors at 3 different heights above ground level: 10 meters above ground level, 500 meters above ground level, and a kilometer above ground level. And we're looking at those in both the Euro 4 and the global. So we can immediately see that the wind patterns and the sea level pressure patterns are much more complex in the Euro 4 because of the complexity of the topography. Whereas in the global model, we can see some smooth sea level pressure contours and some smoothed out wind speed and wind direction contours. What you'll also notice is that the high points, the kind of peak values of the wind speed, which are present in the Euro 4, aren't present in the global model because it's been smoothed out over a larger area. Now, if we take a look at the air concentration that we've then predicted using these two different resolutions of meteorology, we can see some differences in the air concentration. So these plots again show the air concentration at 100, 500 and 1,000 meters above ground level from both the Euro 4 and the global model. And in particular, if we look at the 100 meter above ground level air concentration, we can see a significant difference between the air concentration predictions made using the Euro 4 and the air concentration predictions made using the global. So in this case, we can see that more of the air has travelled northwards when we use the Euro 4 model, and when we use the global model, the air tends to remain kind of where it is, but travel in a northeasterly direction. We can also see that as we get further from the surface, so that topography resolution is less important, that the winds become more similar in the Euro 4 and the global. And so in the case of the 1,000 meters above ground level, the air concentration predictions from the Euro 4 and from the global model are much more similar. So when using MET data, the first thing that we need to be aware of is the resolution of that MET data. And another way to look at the resolution is how big a feature can that MET data resolve. So numerical weather prediction models, NWP models, typically resolve features of about 5 grid lengths. So if you want to resolve a weather feature that's about 10 kilometers across, then you're going to an NWP model with a resolution of less than 2 kilometers. So that's resolution. Now, we would expect that in most cases a higher resolution model would be better, right? Seems to make sense. But it's not always the case. And this is work from a study done looking at upper level winds above Iceland, again for our volcanic ash forecasts. And what those figures show is that for the upper level winds, the global model is actually more accurate when compared to observation data than the limited area or higher resolution model. And that's because they're designed for different purposes. So the limited area models are much better for the near surface plumes, where that high resolution better captures the topography and better captures the local variations in wind speed. But when we're looking at high level winds, high altitude winds, so kilometre or more above the surface, then actually our global model is actually doing much better at predicting where those winds are going because it covers the whole globe and it captures the whole global meteorology. Now, another thing to be aware of when you're using meteorology is that how you use that meteorology in the dispersion model. So as well as a time step in the meteorological model, we also have a time step in the Lagrangian model, and that time step is setting the frequency at which the model queries the metadata. So if you remember earlier, I said that we kind of stop the model, if you like, and each particle goes into the metadatabase and grabs out the wind speed, wind direction, temperature, and other variables. And we can do that kind of once every minute, we can do that once every 5 minutes, we can do that once every 10 minutes. Now the risk is if we do that over too long a time period, so if like say we do it over 10 minutes, then between time steps we might move our particle more than one grid cell. So consider this picture in the top right here. You can see that at T0 we're in this bottom left hand grid cell. We query the metadata and get a wind speed and wind direction, and that tells us to move our particle in a northeasterly direction by this distance. So we can see at the end of the time step, we're in the box in the top right hand corner, and we've completely skipped over 3 boxes there. So we've not covered any of these 3 boxes. And that means that we've missed information potentially in terms of changes in wind direction and wind speed. So we really want, if we're using higher resolution meteorology, we need to shorten our time step so that we capture that meteorology, and so that our time stepping looks a bit more like this bottom right hand picture where we time step through all the boxes en route from the bottom left box to the middle top box. So some examples of time steps you might use for each model are shown at the bottom. So for a 17-kilometre model, a 5-minute time step might be quite reasonable. And for a 1.5-kilometre model, it might be better if you use a 1-minute time step. However, just to be aware that if you use shorter time steps, it will take longer for NAME to run. So there's sometimes a bit of a trade-off, and sometimes we need to say use a 2-minute time step for a 1.5-kilometre model just purely because of the speed or the length of time in which we've got to run that model. Okay, so I've given you a bit of a view of how NAME uses metadata and then how you make the best choice of the metadata you want to use. But rather critical to this question is what metadata is actually available. What metadata do we already have ready formatted for NAME to use? And over the next few slides, I'm going to show you some of the places you might get metadata from and what metadata we have available. So our current metadata that we're using right now operationally at the Met Office, we have two different resolutions of model. We have a global model and we have a 1.5 kilometre model. The global model has a resolution of 10 kilometres at mid-latitudes. It has 70 levels in total, but at the current time we only take 59 of those levels. So although the top level of the model goes up to 80 kilometres, we're actually only extracting metadata that goes up to 30 kilometres. It has a time step of 3 hours and the total forecast length is 168 hours. We're also, for local scale modelling, using a 1.5 kilometre model. It has a boundary which stretches it out to 4 kilometres. We don't use that boundary, we just keep the bit that's at 1.5 kilometres. And again, this model has 70 levels, but again, we're only taking the bottom 57. So we're going up to 12 kilometres rather than 40 kilometres. This model has a 1 hour time step, and currently we have available out to 36 hours, although over time the number of time steps has varied. So that's what those numbers are for there. Now, both of these are big, so the files to cover the whole of the UK or the files to cover the whole of the globe would be rather large files. And if you imagine trying to read a very large file in with a model, you could end up spending most of the time trying to run the model of just reading in the metadata. And actually, we're often just interested in a small area, so we might just be interested in kind of Europe or just Africa, in which case we don't want to read in the whole globe because that would just waste time reading in metadata that we're then ultimately not going to use. So what we actually do is we split the metadata up into a number of domains, which we call parts. They're denoted by PT if you ever look at the name of the file. And this picture just shows you how the global domain sits split up. So PT2 is the area that sits over the North Atlantic and Europe. And then you can see we've got PT1 covers the North Pole, PT14 the South Pole, PTs 2 to 5 cover the Northern Hemisphere as far south as 25 degrees. Then we've got the equatorial region, and then we've got the Southern Hemisphere. The UK is also split up, and the best place to look for how the UK is split up is in the user guide for NWP. The other thing you might notice if you look at the MET files quite carefully is that there are I files and M files. So for every time step, every time-stamped file, you'll find there's an I time-stamped file and an M time-stamped file. And the reason between this is that we have instantaneous files and we have mean files. So some variables we take mean variables and some variables we take instantaneous ones. And the reason for taking means is actually the precipitation. So we used to take instantaneous precipitation, and you can imagine that we had these small scale features, so bands of frontal resolution, and then we only took the files every 3 hours. So what would happen was you could see this feature move every 3 hours and it would just hop. So you would get the position at hour 0 and then 3 hours later the position, and between the two there would apparently be no rain, despite the fact that in reality we would know that that rain cloud had passed over the gap. So when we rolled out NAME 6.3 and when we moved from Mark 6 to Mark 7 global metadata, we introduced mean files so that we could get a much smoother precipitation field. And at the bottom here, you can see the difference between that instantaneous field on the left and the mean field on the right. And I think it's quite clear. You can see the gaps between the rain showers on the left-hand picture. So where might you be getting metadata from? Well, we store a lot of metadata on the scientific server Jasmine, which I think Andrew is going to tell you a little bit about. And so this is really just a reference list of what's available on the Jasmine server. This is the global metadata, and the next slide contains the UK metadata. Data are normally uploaded with a time lag of somewhere between 10 days and a month. I won't go through the details because you can just come back to this slide to see what's there. And then this is the local scale data. So as well as some 1.5 kilometre data, we have some 4 kilometre data from 2007 to 2013, and some 12-kilometre data from 2002 to 2009, and that's all available on Jasmine. So as well as the more recent metadata, we also have a large archive of metadata going all the way back to 1995, depending on the region you're interested in. And this page just lists the so the Unified Model of the Met Office, lists what stores of metadata we have that you can run name on or request to run name on. It's also possible to run name on ECMWF metadata, and we've had collaborators who've run name on ERA 40 data, which runs from 1957 to the present, and ERA interim, which runs from 1979 to the present. So if you're looking further back in time than 1995, or for some reason you particularly need to use ECMWF data, then please just contact one of us and we'll explain how you get hold of ECMWF metadata and how you format that data so that NAME can read it. So that's been a little bit of a whistle-stop tour to metadata. There's a lot to look through and a lot to learn, and I'd really recommend that you take some time to look both at the user guide for NWP and the name user guide to see what you can do with metadata. Hopefully here we've briefly touched on the resolution of the metadata, the region of interest of the metadata you might want, how that might affect the volume of data and the speed of the name run, how name uses the metadata, and of course what metadata is available for name. As I said, if you have any questions about this, please don't hesitate to contact one of us. Thank you.